Hi, this is our CSE 141L video, and my name is Brandon Zito.
My name is Yalu Ouyang.
And my name's Harrison Ka.
Hi, I'll explain our architecture. So, we have a 3-bit opcode and two 3-bit operand registers for each 9-bit instruction. So this allows us 8 total instructions and 8 total registers. So the 8 instructions we chose are NAND, load, store, rotate shift right, move, add, branch not equal to, and set. And of these instructions, all of them are R-type except for set, which takes an immediate value. And we have 8 total registers, 2 of which are special, and these registers are ROUT and RAI. RAI stands for Arithmetic Intermediate and is used only in these pseudo instructions where we implemented it in our assembler. So how our assembler works is taking these more complex instructions and reducing them into a series of NAND instructions. However, we realize that we want to preserve registers A and B, so the input registers to like an XOR, for example. And that is only possible if we designate a special register, RAI, or arithmetic intermediate, to be used for the purpose of preserving registers A and B in more complicated instructions such as XOR. And lastly, for our branch not equals instruction, we decided that we'll compare the two registers in registers 1 and 2, so the input registers, and we'll jump to an exact location at the location of the output register. So this is specified in a module called PC lookup table, so program counter lookup table. So now I'll go over a block diagram of our design. So as you can see, the PC lookup table I mentioned before, and this is an overview of our design. So one thing that we changed that's not in a typical microprocessor is the branch command. So from our reg file to our ALU, we only have 2 outputs. However, for our branch, we need a register for the location where we're going to jump, as well as 2 registers to compare. However, this does not fit between reg file and ALU, so we decided to take an output from reg file and an output from ALU and feed them both into PC lookup table so that the ALU can do the comparison operation for us, and reg file can just tell the lookup table which line to jump to if needed.
Hello, so now I'll be explaining program 1. So as you can see here, in the assembly we have this R0 loop, and this is basically our index for our initial loop here. And this is going to run for every single byte, and we are loading memory from data memory at both I and I+1. We need to calculate the parity bits and format both the data and parity bits into the encoder version and store them into data memory from 30 to 59. This contains one jump loop instruction at the end here, and in between we use a test bench to pass in random values to be processed into data and parity bits. For the test bench, I will first be testing this random shifted by 5. So as we go to model sim, we can see that it works. And we get a program score of 15 out of 15. And to change it up, I will instead use the other test case in which we shift it by 4 as the input. And here you can see our program running, and through the clock cycles, you can also see the data memory slowly getting filled up here. So as you go over time, you'll see all the data memory being filled up properly.
I'm Yalu Ouyang, and I'll walk you guys through the code that we did for program 2. This is roughly split into 4 parts. First, we sort the data points to obtain the data bits B1 through B11. Next, we calculate the parity bits with the B1 to B11. In this part, we use some of the code that we did for program 1. And after we've calculated them, we store them at data RAM 60 to 89. Right, in the third part, we are comparing the parity bits that we got from our calculation with the input parity bits, and we separate them into 4 cases. So if P0 matches and all having good and clean, no errors, if P0 matches and the one or more the having bits, parity bits are bad and there are 2 errors, P0 is bad, all having are good, the parity is bad, P0 is bad, and if P0 bad or Hamming is bad, that means that it's a classic Hamming problem. So depending on that, we set the flags the F1 and the F0. And so if it's 2 more errors, we set F1 to 1, 0. If it's just 1 error, it's 0, 1, and no error, we're good, it's 0, 0. Next, in the final part, we are checking the parity bits to see if it's a parity bit error or data bit error, and we fix them accordingly. Okay, see, that's a lot of statements. Right, so this is how it works with our test bench. So if you look over here and I compile the test bench, this would give us the result. Let me just restart it. Alrighty, you can see the result is 15 out of 15. Now over here, that this part, that's our program calendar. We can see which language instruction we're on, and this contains our registers. This is where we store our calculated results inside the memory. So if I make it larger, you should be able to see. So it's getting written. All right. Now for the other test cases, if I set the flip to be this and recompile. Also, something to note is that we've modified the test bench output messages to make it easier to read, which helped us greatly in our debug process. So as you can see here, it's also 15 out of 15. See, now let me just change it for this final test. The bit is now I+1, and we recompile and run again. And it's another 15 out of 15.
So for program 3, this time we have 3 sections, and the first part is to find a number of bytes with at least 1 pattern. In order to do this, we had essentially 2 for loops, and that was we used 2 branches for that. And as you can see here, the first one loops 32 times, getting all the current bytes, and then the J here in this inner for loop is going to check if the current byte matches the pattern and break once it finds a byte occurrence. For the second part, for program 3.2, we are trying to find all of the program counts of the number of patterns without byte crossings. So essentially, we loop through very similar to part 1, 32 times, but this time, every time we have a pattern count, we continue to find the next pattern, and we don't break out of the inner for loop. And for the last part of the program, 3.3, we're trying to find a number of patterns with byte crossing. So this time we're taking 2 bytes and we're finding basically the left part and the right part of both bytes that match with each other, and we try to find patterns in those. And same thing, we have it in an hour loop, and we just have to mask the top and bottom part of both bytes to find the overlap occurrences. And we add them all up at the end in order to find the correct values to store. Alright, so now I'll be testing program 3. For the first test case, I'll be doing testing for all ones, and the matching string we're trying to find in all ones as well. And as you can see here, the output we get is 128 for patterns by 32 bytes and 252 patterns per byte crossing. Now I'll be testing with 1010s, and the string we're trying to find is 10101. As you can see in this test case, we get different values of 64, 32, and 126, and it matches. For the third test case, I'll be testing the random. And as you can see, we get 336, which does match. And for the last test case, I'll be tested random with shifted random values such as 5 and 3, or 2 here on the bottom. And as you can see, we get 115. I'll also show this in the waveform viewer. So as you can see, the values are being slowly filled in for 33, 34, and 35 over time. As you can see, 35 is being calculated at the very end.
In conclusion, our hardware was designed with limited 9-bit instructions in mind. Additionally, we designed our software to specifically handle useful operations like XOR and rotate shift right to run the 3 specified programs. This allowed us to omit instructions we deemed unnecessary, like subtract, which would increase the number of bits needed for the opcode. As a result, our instruction set is simple yet efficient.